To know the thermal properties of materials, you should be familiar with the properties of molecules. In solids, molecules are closely packed and exert a large cohesive force on each other. In a solid, the molecules are fixed in their position and can only oscillate about their mean position. Due to this reason, solids have a definite shape and volume. When a solid is heated, its molecules gain energy and the distance between their equilibrium position is increased. It causes the solid body to expand a little and is known as thermal expansion. On heating the solid further, the distance between the molecules becomes too large and the force of attraction between them is almost negligible. Now the molecules are free to move inside the solid, which now turns the solids into a liquid. This is known as melting of solids. Now we have to talk about a concept called latent heat. During phase transformation, a solid is converted into liquid. For that, we are applying heat energy, but the applied heat energy may not be used to increase the temperature of the system, but can be used to change the state from solid to liquid. Throughout the process, the temperature remains constant. This is called as latent heat of fusion of the solid. The temperature of the solid remains as that of the temperature of the liquid remains as that of the solid because the heat taken by the solid in melting is used up in overcoming the force of attraction between the molecules and pull them apart. It is called the latent heat of the fusion of the solid. The molecules in a liquid are farther apart than in a solid. They cannot easily leave the liquid, but they are free to move about anywhere within the liquid. Due to this, liquids have a definite volume but no shape. In a gas, the distance between the molecules is too large. Therefore, the coercive force of attraction between them is negligible. This is why a gas has neither shape nor volume of its own. The kinetic theory of gases explains the macroscopic properties like pressure, temperature, and volume in terms of microscopic properties of gas molecules like the molecular mass, diameter, and velocity. See the concept perfect gas. A gas that obeys all gaseous laws without any limitations is called an ideal gas or perfect gas. We know that Boyle's law, Charles' law, these are all the gaseous laws. The molecules of an ideal gas do not exert a force of attraction on one another. The molecules of an ideal gas have only kinetic energy. The kinetic energy depends on temperature. We know that velocity C is proportional to temperature. Once the temperature is increased, the velocity is also increased. Half mc square is proportional to T. The gas equation for 1 mole of an ideal gas is PV equal to RT. For n moles, the equation is PV equal to nRT. The value of gas constant R is 8.314 into 10 power 3 joule per kilomole Kelvin. You may write the same in terms of 8.314 joule per mole Kelvin. Without this 10 power 3, you have to present. At that moment, you should remove this kilo. All real gases deviate from these gas laws, that is Charles law, Boyle's law, so on, to a smaller or greater extent. The nature of deviations is smaller at lower pressure and high temperatures, but large at high pressure and low temperatures. At a low pressure and high temperature, the gas molecules are making their random motion. Therefore, the attractive force between the molecules is negligible. At that moment, a practical gas is similar to an ideal gas. Once the pressure is increased at high pressure and low temperature, the molecules are closely packed. Therefore, they may be subjected for force of attraction. At that moment, an ordinary gas is deviated from the ideal gas. Now go to the Boyle's law. At a constant temperature, the volume of the given mass of a gas is inversely proportional to its pressure. V is inversely proportional to pressure. V equal to constant by P. PV equal to constant. You know that density rho equal to mass by volume. Therefore, we can write rho is inversely proportional to V. According to our Boyle's law, V is inversely proportional to P. From these two relations, we can write pressure is directly proportional to density. That is, P is proportional to rho. Boyle's law holds good for any gas at high temperatures and low pressures. Next, we may go to Charles law. It has two statements. The volume of a given mass of a gas at constant pressure is directly proportional to its absolute temperature. V is proportional to T at constant pressure. So V equal to constant T. V by T is a constant. Second statement, the pressure of a given mass of a gas at constant volume is directly proportional to its absolute temperature. So pressure is directly proportional to T at constant volume. So P by T equal to constant. The product of density and absolute temperature of a perfect gas at constant pressure is constant. Now we may go to postulates of kinetic theory. All gases are composed of molecules. The molecules of a gas are alike but different from the molecules of other gases. The molecules are mere point masses, their dimensions being negligible as compared to the distance between them. Compared to distance of separation, the space occupied by a single molecule is negligible. The molecules are in constant random motion. They have velocities in all directions ranging from 0 to infinity. The velocity of molecules increases with temperature. Between two collisions, a molecule moves in a straight line. The distance is called the free path. The collision time is negligible compared to the time taken to cover the free path. The molecules are perfect elastic spheres and exert negligible forces of attraction or repulsion on one another or on the walls of the containing vessel. Hence, in a direct impact, the molecules begin to move in the opposite direction with the same velocity. Now we may go to the concept of root mean square velocity. The root mean square velocity of the molecules is equal to the square root of the mean of the squares of the velocities of the various molecules. C equal to root of C1 square plus C2 square plus C3 square plus Cn square by n. C square equal to, this is our mean square velocity. This is mean square, but this is our RMS, root mean square. Pressure of a gas is given by the formula 1 by 3 mn C square by V. Here m into n is equal to capital M, mass of the single molecule. If the system contains a number of molecules, m into n is equal to capital M. But m by v equal to rho, density of the gas. Therefore, this relation is modified as 1 by 3 rho c square, because m by v, m into n is our capital M by v is our rho, so p equal to 1 by 3 rho c square. Relation between pressure and kinetic energy. P equal to 1 by 3 rho c square is expressed as 2 by 3 into 1 by 2. 2 get cancelled, we may get 1 by 3 rho c square. But 1 by 3 rho c square is mean kinetic energy per unit volume of the gas, and let it be E. You know that density rho equal to mass by volume. Here we have considered volume is unity. So m is replaced by rho. See here, 1 by 3 rho c square, which is equal to 2 by 3 into 1 by 2. 2 to get cancelled, we can get 1 by 3 rho c square. Rho equal to m by v, but half m c square is our kinetic energy, which is taken as E. But m by v is our rho. If the volume is unity, we may replace this by means of rho. So energy E equal to half rho c square. Half rho c square is the mean kinetic energy per unit volume. Therefore, P equal to 1 by 3 rho c square is equal to 2 by 3 into 1 by 3 rho c square, which is equal to 2 by 3 into E. Hence, the pressure of a gas is equal to 2 by 3 of the translational kinetic energy of the molecules in a unit volume. Boyle's law from pressure. The heat energy of the body is the energy of motion of the molecules. When the temperature is kept constant, the heat energy of a given mass of a gas, and hence the total kinetic energy of the molecules, is constant. Total kinetic energy half mn c square. This is half m c square, which is equal to half rho c square, is a constant. You know that P equal to pressure P equal to 1 by 3 mn c square divided by V. This is 2 by 3 into 1 by 2 mn c square by V, this equation. Then we have proved that P into V, which is equal to 2 by 3 1 by 2 rho c square. Already we have proved 1 by 3 rho c square is a constant. So 2 by 3 is also a constant. So PV equal to constant. Hence at the constant temperature, PV equal to constant. This is our Boyle's law. Perfect gas equation from pressure formula. At absolute zero, the heat energy of the molecules of a gas must be zero. Hence, the kinetic energy and root mean square velocity of the molecules must be 0. When certain amount of heat energy is added to the gas, it will appear as the kinetic energy of motion of its molecule and is given by half mn c square. The rise in temperature T is also proportional to the amount of heat energy added. Hence, half mc square is proportional to T. We know that pressure equal to 1 by 3 mn c square by V. PV equal to 1 by 3 mn c square. PV equal to 2 by 3 1 by 3 mn c square. This mn c square is proportional to T. Then 2 by 3 is a constant. So PV is proportional to T. Therefore PV by T is a constant. PV equal to RT. The SI unit of gas constant is joule per mole Kelvin. Avogadro's hypothesis. Equal volumes of two gases at the same temperature and pressure have the same number of molecules. Avogadro number n equal to 6.02 into 10 power 23 per mole or mole power minus 1. In the kinetic theory of gases, it is assumed that there is no force of attraction or repulsion between the molecules of a gas. Hence, no work is done in changing the distance between the molecules, and the gas possesses no potential energy. The internal energy of a gas is wholly kinetic. Relation between pressure and RMS velocity. We know that pressure P equal to 1 by 3 mn c square by V. PV equal to 1 by 3 into 2 by 3 mn c square, but PV equal to RT, m into n equal to capital M. So RT equal to 1 by 2 mc square into 2 by 3. So take this 3 by 2 here. 3 by 2 into RT equal to 1 by 2 mc square. Now 3 by 2 R by n into T. Divide both sides by capital N. R by n into T equal to 1 by 2 m by n into c square. But m by n is small m. So 1 by 2 mc square is equal to 3 by 2 R by n is equal to Boltzmann constant K into T. From this c square, which is equal to 3 kt by m, then c equal to 3 kt by m inside the root. Now we may present c equal to 3 RT by m. This is another one form from this equation. Here the value of Boltzmann constant is 1.38 in 10 power minus 23 joule per Kelvin. The kinetic energy per molecule is 3 by 2 kT. The mean kinetic energy per molecule in each mass of a gas is proportional to the absolute temperature. Kinetic energy per gram molecule of a gas at absolute temperature T is 3 by 2 RT, where R is gram molecular gas constant. The absolute zero temperature is a temperature at which the linear velocities of the molecules of a gas are reduced to zero. Mean free path. The average distance traveled by a molecule between two successive collisions is known as mean free path. Mean free path is represented by the letter lambda, which is equal to s by n. This distance is the number of collisions. Average time between two successive collisions is given by the formula 1 divided by pi d square c into m. Here d is the diameter of the molecule, c velocity. n number of molecules. Mean free path lambda, which is equal to 1 divided by pi d square into n. You know that velocity equal to distance by time. Distance equal to velocity into time. So if you multiply this time factor by means of c, velocity, you may get our mean free path lambda. In the above treatment, all molecules except one have been considered to be at rest. Only one molecule is in motion, all other molecules are assumed to be at rest. The quantity pi d square is known as the microscopic collision cross section of one molecule and denoted by sigma. Then lambda is equal to 1 divided by sigma n. The number of collisions made by a molecule in 1 second is known as frequency of collision. That is pi d square c into n. Say here this is t. T equal to 1 divided by f. So f equal to pi d square cm. The unit of frequency of collision is second power minus 1. Time of collision, average time between two successive collisions, is expressed in terms of second. Mean free path is expressed in terms of meter. Unit of mean free path is meter. Clausius relation and Maxwell's formula. Lambda equal to 3 divided by 4 pi d square n is our Clausius relation. Whereas Maxwell's formula is lambda equal to 1 divided by root 2 into pi d square n. Mean free path of a gas is inversely proportional to the density of the gas. If m is the mass of the gas molecule, then mass per unit volume or density of the gas is rho equal to m into n. From this, n equal to rho by m. So in this relation, instead of n, if you substitute rho by m, then lambda equal to m divided by root 2 into pi d square rho. From this equation, it is obvious that mean free path of a gas is inversely proportional to the density of the gas. Mean free path in terms of temperature and pressure. The pressure of a gas P is given by the formula NKT. Here K is our Boltzmann constant. From this, N is equal to P divided by KT. Therefore, lambda equal to K into T divided by root 2 into pi d square P. Say, consider the relation lambda equal to 1 divided by root 2. Lambda equal to 1 divided by root 2 pi d square n. In this relation, if you put n equal to p divided by kt, we may write lambda equal to kt divided by root 2 into pi d square into p. The mean free path varies directly with the absolute temperature because T is in the numerator and inversely with the pressure. If the temperature is increased, the free path is increased. Once the pressure is increased, the free path decreases. Degrees of freedom. The degrees of freedom of a system is the number of independent variables required to describe its state or position completely. Monatomic gases like helium, argon, neon, etc. consist of a single atom which can be represented by a point in space. It can undergo only translatory motion. Therefore, its degrees of freedom is 3. X, Y, Z are the 3 coordinates we need. So, the degrees of freedom of a monatomic gas is 3. A monatomic molecule can also rotate about its own axis, but its moment of inertia is so small that its rotational kinetic energy is negligible. So it has only 3 degrees of freedom. Diatomic and polyatomic. The molecules of a diatomic gas like N2H2O2 consist of two atoms connected to each other by a rigid bond-like dumbbell. Such a molecules can perform not only a translatory motion but also rotate about any three mutually perpendicular axes. But its moment of inertia about the axis joining the two atoms is negligibly small as compared to that about the other two axes. Hence, it can have only two rotational motions. Therefore, a diatomic molecule has 5 degrees of freedom, 3 translational and 2 rotational. But in the case of polyatomic molecule, the degrees of freedom is 6. Polyatomic molecules like CO2 and CS2 can rotate about any of the 3 coordinate axes if the 3 atoms are placed at the vertices of a triangle. Thus, it has 6 degrees of freedom in all, 3 translational and 3 rotational. Now we have talked about the law of equilibration of energy. This law is about the distribution of thermal energy among the molecules of a gas. It states that the total energy of a dynamical system in thermal equilibrium is distributed equally among its various degrees of freedom. The energy associated with each molecule and each degree of freedom is 1 by 2 kT. The principle of equilibration of energy is applicable for those degrees of freedom for which energy is expressed in terms of the squares of the position coordinates, that is x square, y square, z square, or the velocity coordinates, vx square plus uy square plus vz square, like that.